I'm going to use my mobile phone also to keep up the timing, because I'm very bad at this. So, okay. Thank you to the organizers for inviting me here. I was actually very excited to take on the challenge of speaking to you about characterization of catalyst, until I realized that I had only 30 minutes to speak about that. So unfortunately, that was a week ago, and then I also realized that it's not possible for me to cover all the areas of characterization of a catalyst. So this is why I have slightly changed the title of the presentation, which is where I decided to turn down to my personal view and recommendations on how can we characterize our catalyst, some tips and recommendations about things that we can do and things that we should not do for the characterization of a catalyst. And I'm speaking about the heterogeneous catalysis, so it will be mainly solids today because of the sake of timing. I've tried both ways now, so is there any? Oh, it's. Okay. Yes, much better. So first thing first, some literature that I would like to pass on to you. We've been speaking a lot about how difficult it is sometimes when we don't give details on comparing data. It's true, it's very true. This is why we have to nowadays pay attention a lot of at normalization. But also, it is true for the characterization of the catalyst. We must be careful. And if we want to compare our data, even just if it's only for the characterization, with the data that has been published or even not published within a project, we have to be careful and we have to read what is being said or recommended. Guidelines, of course, are imposed by IUPAC. I've just shown in here just a few examples on. I'm sure that maybe the IUPAC has more updated reports on at least the catalyst characterization. I was handling this one from 1991, which is already very good. It's giving you a lot of information on what you should be looking at when you're characterizing your material. Also, some other, just pick out of the literature some other interesting papers, books, and reviews that I think it could be of interest. I'm going to give a copy, not of the whole presentation, but of at least the part that I can disclose to the organizers. So there is no need for you to copy all these references if you don't need to. First of all, some words that I've liked to some reflections that I'd like to make out loud. When we are trying to characterize the catalyst, we have to think first. So we have to maybe think about these things that I've indicated there. So which techniques do I need to use? Of course, you can answer yourself saying, no, as many as I can, and those that I can see in the literature. But it's not really that the thought that you should have in mind. You have to think first about what type of information you want to have from your material. And once you have identified that, maybe you can go to different characterization techniques. So the tip here is to select the techniques, in plural, that helps you to gather the information that you're actually looking for and not just get lost in the middle of I'm going to use all the techniques in the world or even all the techniques that I have in the lab. Really, this is very important. It is one of the defects that young people has when they're starting to do the PhD. So I'm going to characterize everything. Well, yes and no. The second message that I want to pass is that there is, unfortunately, no single technique that will give you all the information that you are looking for your catalyst. So you have to think wise, but at the same time, you have to select and to realize that all the techniques are complementary. And this is a message that I want you to take home today. I have provided here just a list of some examples of techniques that are widely used for characterizing a catalyst, no matter your application is. But you have to consider that all of them are complementary. So even if you have identified what is the information, the piece of information that you are interested in having, you have to think that one technique will not give you the answer. So Complementary, yes. Just doing them all for fun, maybe not a solution. So, as I said before, I already ran out of time. So I decided to speak about just selected techniques, morphology because I think it is important, porosity and process distribution because it's one of my favorite topics, and I think it's also very important in catalysis. And then I will not have time, so I could take requests from the audience. So either surface chemistry and composition, that's why I would appreciate if the chairman tells me 5 minutes before we are to the end, and specific properties of catalyst sites. And I have just a few examples about optical band gap and the estimation of the potential of the edges of the conduction band and the valence bands in photocatalyst. Morphology, very fast. It is very important to consider the morphology of our catalyst, even though if you have a procedure that has been repeated in your group and you know what you are expecting during the synthesis, you still have to check if there has been everything according to what you were expecting. And this is some flavor of the type of information that you can have. Of course, particle size and particle shape, which is important because it might have something, somebody raised that. It might have, you're working on the nanometric scale, some ecotoxicological effects, and then you have to think of that also. If you're working with a support and you are dispersing a catalyst on top of it, you can also have an idea of what is the dispersion and the degree of agglomeration by using morphology analysis, both in the micron and the nanoscale. And it is important also to think about whether if you want to use SEM or TEM, depending on the scale. So these are not the same. The principles, we don't have time to go there, but you have to think of whether if you're looking to have an idea of your catalyst at the micro scale or the nanoscale. These are just examples of materials prepared in our group where we can see also these topologies of going from nanorods to these spherical shapes, which can be dense or not dense. And there's some information that can also help you to understand why your catalyst is behaving as he is doing. One example is that these SEM and TEM techniques, in my opinion, are really very dangerous because sometimes we tend to show what is how the beautiful part of our catalyst. So don't be ashamed to show also the parts that might not be so beautiful because those are helping you to understand the catalytic impact or performance of your material. These are just a few examples combining SEM with EDX, where we can see the distribution of the different atoms in the catalyst. And as you can see here, if I show you just this part of the material, you see these nice, almost homogeneous spherical or pseudospherical particles of the catalyst. But if we look closer in a different position of the same sample, we have observed the presence of platelets and a different shape of the catalyst. When we finalized this with EDX at that time, we have seen that there was a different distribution of the bismuth tungsten oxide, which was our catalyst, and this was due to the formation of a second phase, an oxide of bismuth alone, indicating that the activity of this material was going to be different as it already was. In this case, this different morphology was driven by the modification of the amount of an additive, a carbon additive that we have used. Of course, coupling morphology with the XRD is very important. I'm not going to spend much time on this. And now I will speak about porosity and process distribution. Here you have the definition of porosity and the definition of the texture according to IUPAC, and then you have the site of the recent report, technical report of IUPAC, which was published in 2015. You have to consider that nowadays we all want to use the word nano for everything. So IUPAC has also considered this, and they have defined nanopores as those lower than 100 nanometers. They still keep the old nomenclature, which is something that we will see in a minute, but we have to be aware of how IUPAC is recommending to use or to label the things in order to not just invent new words. When we speak about the porosity, of course, what we're looking at is actually not the material itself, but the space which is inside the material, those empty voids in the materials. We might be interested in having specific surface area, total pore volumes, and PACs, pore size distribution, as we will see. But also, it's important, particularly in catalysis, to have these two concepts in mind. When we speak of surface area of our material, are we meaning internal or external surface area? These are not the same, and they might explain why your catalyst is working or performing in one way or the other. Here you have a definition according to IUPAC. Internal surface area, it's what I've tried to indicate in here in this surface, which is the cracks or the voids that are deeper than they are wide. And they have to be accessible to a probe in order for you to measure it. The external surface area, it's more easier to consider, and it usually takes into account the irregularities of the sample and also the surface roughness. But the main difference is that it accounts for the cracks, which are wider than they are deep. And there are different methods that have to be applied in order to get the estimation of what is the internal and the external surface area of your material. Going again to the definition of the pores, even though all of them are nanopores, below 100 nanometers, they still decided to keep the old nomenclature based on historic reasons, and this is the classification according to their sizes. 2 nanometers micropores with an I, between 2 and 50 mesopores, and over 50 micropores. This is important because the confinement of your molecule, if you have a porous material, it's going to be very much dependent on the size of your pores. And in the case, the mass transfer is also going to be very much affected by the size of the pores, particularly when you have materials which are highly mesoporous. You also have to take into account that, and we will go to see that by SEM or TEM is not possible to see all the pores. I've read many times in the literature, so as we can see in this SEM picture, I have micropores in my material. You cannot see them. It's just a matter of resolution. So remember, with an SEM, even if it's a FISM, and you have a strong resolution, you can no lower down than 400 nanometers. And micropores are these, so you will never see them. Even by TEM, you can see macropores, you can see mesopores, and it's very hard to see micro, lower than 2 nanometers. So you have to use different techniques. Which techniques are used? Gas adsorption. This is just a typical recommended experiment that IUPAC is encouraging you to determine the porosity and also the pore size distribution, including surface area and pore volumes of your materials. There are some implications depending on the shape of the isotherms that we do not have time to go over that, but it's pretty much related with the mechanism of adsorption and distortion of the gases inside your material. And also with the fact that the adsorption and the desorption follow a different mechanism, and that will be translated in a different shape in the isotherms. So for those of you, how many of you are working with nanoporous or porous catalysts? Can you raise your hand? Okay. So I'm sure that you are familiar with this. This is the new IUPAC classification, as I said, revisited in 2015, so please do not use the old one. They basically rearranged the name, including the appearance of new shapes due to the advance in the formation of materials. And depending on the shape of your isotherm, you are going to have the first indication on whether if your material has micropores, mesopores, or other type of pores, even without applying any equation. Then, if you are more trained to the analysis of this, you can also analyze the shape of these hysteresis loop on the adsorption and do a classification and gather some extract information about how the pores are connected or not in the matrix of your material. And then this is just a few examples of real cases. These are the nitrogen adsorption isotherms of a series of nanoporous carbons with different Burnout degrees, which means that we have been enlarging the pores. So I've indicated it in here, but I hope that it's clear that we have what the IUPAC is labeling as type 1. And not only that, we're going from type 1A to type 1B because the shape matches, and that's already given us a lot of information about the pore structure. So another example, and my student here already know the answer. So if we have these two isotherms, and if we compare with the classification, we could say, okay, so they might be type 2 or type 4. Which one is it? This is a very common mistake on the analysis of materials with a very low porosity. So you have to look first at the shape, but also if you've realized, have removed the axis from it. The amount of gas adsorbed is also an indication on the porosity of your material. So if you have a low pore volume, which is the green one, it will be most likely a type 2 isotherm, which is due to a material with a low porosity. But if you have the same shape with a much higher pore volume or amount of gas adsorbed, in this case, you have a material with micro and mesopores, and therefore you will never have a type 2 isotherm. They're pretty much alike, but you need to look at all the information that you have. And then you can apply different equations if you want to gather the PSD. Doesn't matter. First information is what you have from the experimental data. Also, you can have an impact of your particle size. If they are spherical and very small, you can have artificial pores, which are actually just interparticle porosity and not inside the particle. You have to be careful, and this is why you have also to combine different techniques in order to have a complete view of your material. So then you have a catalyst, and you think your catalyst is porous. So what do? You want to analyze it. So the first choice is, what gas do I take? Because IUPAC recommends many of them. Well, it depends on whether if you are in the States or in Europe, because you can use nitrogen at 77K or argon at 87K. But in Europe, argon at 87K is very expensive, although now the things are much better due to the presence of cryostats. And mostly all the people uses nitrogen at 77K, but in the States it's more easy to get argon, so it really depends. Then you have these different, well, this is corrupted, but I should set a volume adsorbed. You have these different isotherms, so, and even if you cannot classify them, you would say, okay, so I have a porous material, the pink, the blue, and this is non-porous. If you stay there, you will be making a mistake. So whenever you have no pore volume adsorbed on nitrogen, you have to, and you must do another analysis in order to confirm whether if you have pores or not. And this is what you have in here. This is the nitrogen adsorption isotherm of this one, of the blue, that I've superimposed, but then I've reduced the range. If you use CO2 at 273 Kelvin, you will see, in fact, that all your materials have the same porosity. And what you just have discovered is that all of them are porous. But this one is a molecular sieve, because as I've mentioned at the beginning, you not only have to you have to be able to measure the voids. And the voids will be accessible depending on the size of the gas that you use to measure them, but also on the temperature because of the kinetics implications. So here I will leave you also some tips on why this second analysis of CO2 at 0 degrees C can also be interesting in order to discriminate whether if your material has pores or not. Then the second question is, okay, so how much sample do I need to run my isotherm? That's a question that I get very often. So it will depend on your material. Because if your material has, or you expect it to have a very high surface area, then you will have a very large amount of volume adsorbed, which is what you're measuring experimentally. So the mass of the material that you need is not that high. However, so if you do the calculations of the estimated error that you have, the minimum surface area that you can measure with most of the equipment is 10 square meters. So if your material has 2,000 square meters per gram, with 5 milligrams, you would have enough. However, you have to place the 5 milligrams inside the tube holder, the holder of the sample, which usually weighs is 35 or 50 grams. So you also have to take into account the mistake, the error, which is associated to this imbalance of the weight. The third question would be, how should I prepare the sample? This is the question that you usually get from the person that is running the experiment for you. And then he's asking you, how can I treat your sample? Well, again, if you go back to IUPAC, you will have some indications on how you should treat your sample regarding the conditions of vacuum and temperature, because you have to outgas your material. You have to clean it in order to get all these empty space available. Why is this important? Because if you go too high, too low in temperature, you will not be removing the moisture which is trapped in the pores. Because it's trapped, actually you need to apply a higher temperature under vacuum in order to remove it. But if you go too high, as in this one, you may destroy or modify the composition of your material. So you need to perform extra experiments in order to identify that, and that the operator of the gas adsorption measurements does not know how to answer. Only you have the knowledge on the material that you have. Then another important thing is whether if you need high or low resolution data, which simply depends on the equipment that you have. The answer for this is very simple, actually. It depends on what is the data that you want to extract. Because these are the isotherms of the same material in two different equipments, high and low resolution. Very same sample. If I plot them in a linear scale, you will see that they're the same, as they should be. But if I plot them in a log scale on the relative pressure, you see that this is high resolution and this is low resolution. So in order to get the shape of the isotherm and the total pore volume or the surface area, low resolution is enough. But if you want to have the complete pore size distribution within the 0 and the 50 nanometers, you cannot use low resolution. You can, and then you have the access to the software of the equipment, and then you can apply all the methods that the software has. But you shouldn't, because you will get non-reliable data. Be careful with just applying all the methods that are uploaded in the software of your equipment, because the software is not telling you whether if you can apply them or not. Then, for the calculation of the specific surface area, it's a very simple calculation. I will skip a few, I'm already running out of time. The most widely used technique is the Btw equation, which is not perfect. Everybody knows that, but everybody is using it. So whether you like it or not, you just have to know that even if you are overestimating the values, still it's a parameter that if you know how to apply the equation, you can use to compare your material with other materials in the literature. It's this equation, which is not linear, but it can be linearized. Then you have also to you have to choose the equation that you're using for linearizing. Of course, again, you go to the software of your equipment, and you don't even know which is the equation that you are using for linearizing. So you simply apply for the report, and then you get a magic number. So 323.25. That might be correct or not. It's up to you to apply IUPAC selections rules to comply and to find which is the right range for calculating the BET. Because that's the equation of the BET, and these are the data of your isotherm. In my case, I'm using high resolution data. So is this an equation that you apply to all the isotherm? The answer is no. This is just the data, and if I plot here my equation, I just mentioned that it should be linear. So if I start plotting from the very beginning of the relative pressure, I do not have a linearity. So you have to know where this equation is applied. So if you keep going, there will be a place where, which is usually between 0.001 and 0.35 of relative pressure, where the Btw equation should be linear. And I mean should be because it's not always the case, meaning that if your material cannot be fitted into this equation, don't even bother. The real experiment is the isotherm, not, sometimes you simply cannot estimate the surface area by these different equations. Of course, what I've mentioned before of complying with the selection rules of IUPAC, it's not only important to have the value of the Btw surface area, but also to check the other parameters of the equation. And this is one of the most common mistakes that it's even unfortunately found in the literature, which is reporting the constant of Btw with negative values. So this cannot happen because it's the constant of Btw is a measurement of the affinity of adsorption. If it's negative, it means that there is no adsorption. So how come that you measure it from an adsorption isotherm? It's contradictory. So please check all the numbers and just be aware that the fact that you have an equation does not mean that you can apply. There are some other methods for the determination, also the Pore volume. I will skip this because I think this is also interesting. I've mentioned before the difference between the internal and the external surface area and how important it might be for describing the performance of a catalyst. There's many different methods in the literature. I've just picked one because it's very commonly used. It's a T-plot method. It's also usually available through the software that you use when you run your gas adsorption isotherm. And there is some things that you have that you need to know. The equation looks like that, and you need to have a reference material. And there is a place in this software where you can actually, you have to select which is your reference material. If you don't do that, you might be, for instance, not selecting anyone, so the numbers that you can get, you still get numbers, but they're not meaningful, or you can just select maybe a reference material of a silica or of a carbon, and your material is not, or of an alumina, so you have to know which reference material is needed. These reference materials are usually complying with these two criteria, which are, have similar chemical composition and values of the affinity for the gas. And there's many of them in the literature, and as I said, you just have to realize that you have to pick one. As in the case of the Btw surface area, this is not applied to the whole range of data. You have to fit your data. So if you have high resolution gas adsorption, you might not be able to use all the points, and you have to be aware of that. Usually, the type of plots that you have are like this. When you are plotting here the thickness, the parameter T versus the pore volume, and you have these shapes, which by extrapolation, they will give you the volume of the different pores, depending on their size, and by a simple equation, you can calculate the surface. Depending on the range where you are measuring this, you get the external surface area or the internal surface area in a very easy way. I have, 3 minutes? Okay, so help me out here. I can speak a little bit about surface chemistry and composition and give you some idea of different techniques that you can apply to evaluate this surface chemistry, acidity, basicity, and things like that, or some specific properties of catalyst sites, mainly optical band gap and determination of potential values. So anyone make? Okay, so let's go to the end. You see, I was very optimistic when I considered that I have more time. Yes, here we have specific. It was mentioned in some talks, at least in one of the talks that I attended, that we have to control, when we have, again, a porous catalyst, we have to control the amount adsorbed. How can we control that? We have to perform a study on the adsorption capacity because it can really change, and it does not even change the confinement state of your molecules or the subproducts that you have, but also it can change the interactions with the surface of your material. This is an example for two carbon-based materials, just for you to see their different parameters regarding texture and also acidity or basicity, as you can see here in the pH. And these are examples of the adsorption capacity of these two materials for different compounds, phenol, paracetamol, and another pesticide that I don't remember right now, TBA. So, and this is the typical adsorption isotherm that you get. So it's very different. Even if the porosity of your material is the same, the acidity of the material can determine very largely the amount adsorbed. Optical band gap. Yeah, I'm sure that you are all very well aware of how the optical band gap in semiconductors is determined. And most of us, we use this diffuse reflectance spectral photometry, where you can have here the equations and the theory that is applied, and why we apply this theory of the diffuse reflectance when we have solids because of the dispersion of the particles. So also, the first thing that we have to consider is, okay, so I have the measurements of the diffuse reflectance, but then I want to extract the band gap energy. So the first question for that, you have this very famous tau plot representation, where you have an exponent that you have to define. So first question is my catalyst a direct or an indirect semiconductor? So it depends on the mechanism of force. And if you're working with TiO2, there is a lot of literature about this behavior. But if you're working with hybrid catalyst or with a new catalyst, you might not have a very straightforward answer. So we will see a little bit of that in later. So the first tip that you can have, I'm not saying it's a definitive one, is the shape of the measurement that you get when you do the diffuse reflectance. This is a part of the work of my student Getanek, who is here today. And then this is just the two examples that I found in the literature where you can see different oxides, and even the magnitude of the absorption coefficient is already a very good indication on the type of mechanism that is happening when you expose, in this case, your semiconductor to light. That is just the first indication, as I said. Another evidence, you can have it by electrochemical techniques, if I can get there, and we will see in a minute. Then you said, okay, easy peasy, I have zinc oxide, so I know what type of semiconductor my material is, and then I record the spectrum, so you just have to choose where you apply the tau equation. In this case, when you have a very well-defined band gap, it's very easy. Nobody's going to make a mistake. Here I've marked in different colors also the experimental data and how they look like when you represent the tau plot. So you see, and then you have to just be careful with the range of the data that you take, but then you do the extrapolation and you get the numbers of the band gap, which are pretty much in agreement with the values that you can get. Here you have the different values that we have evaluated depending at different wavelengths, and still the standard deviation, which is pretty good. So another method is when you don't have enough sample, then you decide to do dilution with barium sulfate. And it's been widely reported in the literature, but not many people actually showing what happens with the data. So these are the different spectra, just the spectra as we record them for different compositions of the same semiconductor as before, if you dilute it instead of using the pure zinc oxide. If we look at the data, they seem to be very different, but actually when you calculate the tau plot and you estimate by the same equation as before, the band gap, we have that the method of the dilution is still valid because this is just a trap for the eye. When you transform this into the tau plot, actually the numbers for the band gap that you get are not so different. But what happens now if you have a catalyst, which is not a very good light absorber as TiO2 or zinc oxide? Well, you might have a very ill-defined behavior, which is what we have plotted here, The scale is different, as you can see. This is for zinc oxide, and this is for a material which is not very good absorbent. You can still see the gap in the representation, but in this case, you have to, because the numbers are actually very different, you must use a double linear fitting in order to get the estimation of the band gap. Another, do I have some more time? No? Okay. So, another interesting technique that you can apply are electrochemical methods in this case. Why? Because when you expose them, a catalyst in a solution, you have the formation of this depletion layer, which you can see in here. You have a potential that is created in the material. So you can actually measure this potential. And when you apply light, as you can see here, you see a drop in the potential. This potential, once you measure it, is you can calculate the potential corresponding to the onset of the photocurrent, which can be assimilated in most of the cases, although it's not for all the samples, to the flat band potential. And that flat band potential would correspond with the situation when the band and the potential of the solutions are even. That can correspond, as you can see in here, with the potential of the conduction band. And if you know the gap, the band gap that you have evaluated by diffuse reflectance, then you can very easily do the maths and extract the potential of the valence band. I'm already run out of time, so unless you have plenty of questions, I have to stop here.
Thank you very much.
Thank you.
Thank you very much.